All right, it's noon. We can get started. So greetings from Computer Science Department at Rice University. Thank you for joining us in the exciting event. This is the first event of 2021, and seeing the excitement, I believe we will have a very wonderful year ahead. So let's go over the logistics. We will have an opportunity to ask question to our distinguished speaker, and we will use the Q&A feature of the Zoom. So if you will hover your mouse down, you will see Q&A and chat box. Remember, the chat box will not work. You can type in your question in Q&A whenever you want. And towards the end, time permitting, we will see how many we can get answered from our speaker. So with that, I would invite our Dean of School of Engineering, the new Dean of School of Engineering, Professor Luai Nakale, to introduce our distinguished speaker.
Thank you, Anshu, and hello, everyone. My name is Luai Nakale. I'm a professor of computer science here at Rice University and also the Dean of the School of Engineering. I want to welcome all of you to this very exciting colloquium. Today is World Logic Day. The UNESCO, in association with the International Council for Philosophy and Human Sciences, proclaimed this day to enhance public understanding of logic and its implications for science, technology, and innovation. To celebrate this day, we are very excited to have one of our own faculty here at Rice, Professor Moshe Vardi, to give a colloquium that traces the path of logic in computing that, interestingly, as Moshe will show, goes back all the way to Aristotle. On a personal anecdote, I've been a colleague of Moshe for 17 years here at Rice University. However, I heard about Moshe since I was an undergraduate student when I took a course on formal verification, where I learned about temporal logic and I got to know about Moshe's work in this area. Moshe Vardi is a university professor, which is the highest title a university can endow on a professor. He's also the Karen Ostrum George Distinguished Service Professor in Computational Engineering at Rice. Moshe is one of the world's foremost experts in automated reasoning, and automated reasoning is really grounded in logic, and that makes him an ideal person to give this talk on this occasion. Moshe holds many honorary titles and is the recipient of too many awards for me to name here, but these also include, for example, in the area of logic, the Goedel Prize. It also includes the ACM Kanellakis Award and many, many other awards. Moshe's work is heavily influential in the field, and his papers have been cited over 50,000 times. It is now my great pleasure to introduce my colleague, Professor Moshe Vardi. Moshe, the floor or Zoom is all yours now.
Cyberspace. Thank you very much. Thank you, Anshu, and thank you, Lue. So today is World Logic Day, as Lue explained.
Moshe, you are muted.
Okay, again, can you hear me now?
Yeah.
Only problem, okay, something is wrong with the navigation. Okay, now I can navigate. Okay, so today is World Logic Day and proclaimed by UNESCO. We need to check what other international day has been proclaimed by UNESCO, I don't know. But what's special about this day is it is the date of the death of Kurt Gödel on January 14th, 1978. It is also, Kurt Gödel will play a major role in this lecture. It is also the birth date of Alfred Tarski, another major 20th century logician. Unfortunately, today I would not have time to talk about Tarski, but Gödel will play a prominent role. What's interesting also about this lecture, it's the first time that we're giving such global lecture and where we are leveraging the power of technology, both the Zoom platform that enable us to reach globally, and also the power of social media to advertise in a very global way. And so far, what I'm seeing is that we have, and the number are still going up, but we have over 850 participants in this seminar. This is, of course, the largest audience I've ever spoken to. And I could even speculate that this might be the largest audience ever in the history of the cosmos for a lecture in logic. And I find it actually quite mind-blowing and something that we need to wrap our brains around. I'm going to talk about logic here from a very specific computing, from the lens of computing. And I mentioned Aristotle, I mentioned the iPhone. So I'm going to put here the logo of the Apple Corporation. And of course, it's an apple and it's a rainbow, and there is a bite in the apple. And people always have speculated, what does the bite in the apple symbolize here? And I will come back to this question towards the end of the talk, just something for you to ponder about. And the connection, there is a connection between logic and computing, which I will describe today. And I will start it with a quote due to my colleague Georg Gottlob, who 2 hours ago gave also a talk, a World Logic Day talk at Technical University of Vienna. And he wrote in 2004, computer science is a continuation of logic by other means. Of course, paraphrasing from Clausewitz, who said war is a continuation of diplomacy by other means. So he's claiming here a continuity between logic and computing. And if you think about it, this is actually a rather puzzling connection. And if to put it very bluntly, if you think about logic, people think about it as some obscure corner of philosophy. And what does an obscure old intellectual discipline have to be with the youngest intellectual discipline, the discipline of the iPhone and Facebook and what have you? And this puzzle has been also raised some years ago by Cosma Arshalizi from the Santa Fe Institute, who wrote about logic in the 20th century. And he put it in a very provocative way. He said, if in 1901, a talented and sympathetic outsider had been called upon, say by grant-given agency, to survey the sciences and name the branch that would be the least fruitful in the century ahead, his choice might well have settled upon mathematical logic, an exceedingly recondite field whose practitioner could all have fit in a small auditorium. There are more people now attending the seminar than people doing logic in 1901. It had no practical application and not even much mathematics to show for itself. Its crown was an exceedingly obscure definition of cardinal numbers, whatever they are. But before answering the question about the connection between logic and computing, we actually have to ask a more basic question. What is logic? It's not so easy to define what logic is. And in a quest to find a good definition of logic, we may go to the most famous logician of all time. This is the Reverend Charles Ludwig Dodson. And if you are know enough about literature, realize he's not famous as a reverend. In fact, you may not necessarily have heard the name, but he is the real person behind Lewis Carroll. His literary name is Lewis Carroll. And of course, through the books, Lewis Carroll, I would say, is probably even more famous than Aristotle, I would speculate. What many people don't know, that Alice was not an imaginary character. He had a young friend, Alice Liddell. And Alice in Wonderland was the first, before it was written as a book, was stories that he was telling his young friend, Alice Liddell. So we can go through Alice and we can find a definition of logic in Alice through the looking glass. Contrary-wise, continued Tweedledee. If it was so, it might be, and it were so, it would be, but as it isn't, it ain't, that's logic. You might define this satisfactory whimsy, but maybe this definition whimsy, but maybe not satisfactory. This is a 19th century definition, so you may want to go to a 20th century definition. And I found one in a book by Andrea Nye, a feminist writer. The book is called Words of Power, where she writes, logic celebrates the unity of a pathological masculine self-identity that cannot listen and recognize only negation and not difference. Again, you might be amused by this definition, but not find it fully satisfactory. So it turns out if we want to find a good definition, maybe we need to go back, way, way, way back to the 4th century BC, where we are going to meet the Greek philosopher Aristotle, that I think deserves the title of being the most influential intellectual ever. His wisdom, the thing that he wrote in the 4th century BC, for almost 2,000 years, there were no challenge. Only maybe during the Enlightenment, people dared to challenge what Aristotle said in the 4th century BC. So Aristotle wanted to understand what distinguishes philosophy. Philosopher literally means philosophia. Philo, it means lover of wisdom. What would distinguish philosopher from demagogue? And demagogue literally means, dema is people, the leader of the people. Some things never change. Demagogue literally means leader of the people. So what does distinguish philosophy from demagoguery? And again, 2000 years later, Francis Bacon would say logic differs from rhetoric in this, that logic handles reason, exact, and in truth. And rhetoric handles it as it planted in popular opinions and manners. So when I teach a course on every fall, I teach a course on logic in computer science. And we start with discussion, what is logic? And I tell the student that logic is about the quest for truth. That's what it is about. We are seeking truth. But Aristotle made an astounding discovery, and this is of formal reasoning. What does formal reasoning mean? So Aristotle wrote a book called Organon, and Organon means tools. This was philosophical tools, so to speak. And he argues that reasoning takes certain forms. And there are classical templates that are called, of reasoning that are called syllogism. Lewis Carroll, again, whimsically called them syllogisms. But the syllogisms are patterns of reasoning, or forms of reasoning. You're all familiar with all humans are mortal, all Greeks are human, therefore all Greeks are mortal. However, and of course we all recognize that this is valid reasoning. Now, we can also substitute and say all Bujums are Slizy, all Tovs are Bujums, therefore all Tovs are Slizy. And this is equally valid reasoning, even though you probably have never seen a Bojum, and you've never seen a Tov, and you have no idea what is Slizy. Again, this is all nonsense term from Lewis Carroll's Jabberwocky. But the form of reasoning is the same, and therefore this reasoning is equally valid. And what comes out of it is the truth comes out of form. And this is an astounding discovery, because usually we think the form is superficial. You have to look inside to find the truth. And Aristotle discovered the truth come out of the form. And this is why we talk about formal reasoning and formal logic. Form is actually very, very important. So this is one major discovery by the Greek philosophers. The Greek philosopher also loved paradoxes, because they found that paradoxes are a way to sharpen the mind and try to find the essence of what is going on here. Why are we getting a paradox? And the most famous paradox is due to Epimenides, who was a Cretan, and he said all Cretans are liars. In fact, many people don't realize that this actually is a New Testament. In the Epistle of St. Paul to Titus 1:12, he said, one of themselves, a prophet of their own, said, Cretans are always liars, evil beasts, lazy gluttons. We don't call them the glutton paradox, it's a liar's paradox. And in fact, we find even a precedent to that in Psalms. Psalms 116:11, the psalmist writes, everyone is a liar. But to get a paradox, you have to sharpen it. It turns out that this by itself does not give you a paradox. And this was done by Eubulides, who said, this sentence is false. This is the liar's paradox sharpened. This sentence is false. So is this sentence true or false? And you realize if it's true, it must be false. But if it's false, it must be true. So what's going on here? What is the truth value of this sentence? And the key feature here is self-reference. And if you want to have some to play with it, try it on kids, because if they're too young, they cannot comprehend the paradox here, and they say, well, I just want to play. But somewhere around maybe 10 or 11, or if they're brighter, maybe even a bit earlier than that, they'll realize this is a real conundrum. Is it true or is it false? What is going on here? And we'll see that this self-reference, the sentence talking about itself, is a crucial theme that will repeat again and again and again. After Aristotle, the Stoics continued to develop propositional logic, but medieval logic is generally not considered very interesting. There are some exceptions. Avenidas, I'll mention Ramon Lull. Ramon Lull was a Catalan monk that lived in the 13th, 14th century. He's one of the people that didn't die young. You can see he lived actually to 83, but we will see shortly how he died. And he was actually quite a sinful man in his youth, but around age 30, he had an epiphany. He became very, very religious. And his quest was to convert the whole world to Christianity. They all need to see the light. And he thought that the best tool to convert people to Christianity would be logic. So here's an argument why you should all believe the Holy Trinity. Listen very carefully. If in thy three properties there were no differences, the demonstration would give the D to the H of the A with the F and the G as it does with the E. And the K would not give significance to the H of any defect in the F or the G. But since diversity is shown in the demonstration that the D makes of D and the F and the G with the I and the K, therefore the H has certain scientific knowledge of thy holy and glorious Trinity. Did I convince you? Maybe not. In Francis Bacon wrote, some persons more ostentatious than learned have labored about a kind of a method not worthy to be called a legitimate method. Begging rather a method of imposture would nevertheless, would no doubt be very acceptable to meddling wits, such as was the art of Lull. So obviously, Francis Bacon did not think very much of the art of Lull. Why is it called art? You'll see in a minute. In fact, Francis Bacon was not the only one. Lull went to North Africa, tried to convert Muslim to Christianity, and they so much disliked his logical argument that at age 83, he was stoned to death. This is a Renaissance painting, anonymous Renaissance painting showing the stoning of the philosopher Ramon Lull. But maybe Francis Bacon was not fair enough to Lull because there is some merit on what Lull was doing. So in 1275, he published a book, Ars Magna Generalis et Ultima. General, what is it? Great, general, and ultimate art. This is a nice title for a book. Consider it for maybe your PhD dissertation. And it turns out that this symbol that we saw in his argument, that some nonsensical, are actually abbreviation. And there's something underneath them. Truth, I is truth, K is glory, etc. B is goodness, etc. And what Lull realized, that when you do logical reasoning, you have case explosion. You have many cases to reason about. And he actually came up with diagrammatic and mechanical aid where you can generate all this, now we call it exponential number of cases to consider. So the value, even though much of what Lull wrote was nonsense, the value is that as far as we know, he's the first person to think about mechanical aid to reasoning. Of course, people who do mechanical aid to computation, abaci, are much, much older. But as far as we know, Lull was the first person to think of mechanical aid to reasoning, that reasoning could be mechanized. And this idea ended up very influential for our next character, which is Gottfried Wilhelm Leibniz in the 17th and 18th century. And many of you know him as one of the co-inventor of the calculus. In fact, he had a huge, colossal fight with Newton over the priority for the calculus. The answer is they both deserve credit, but it was a very ugly fight. But he also developed binary notation. And as such, we can fairly say that he's the inventor of the bit, which is a central element, of course, today in computer science. Now, Leibniz was quite a prodigy. He taught himself Latin at age 8 and started reading Aristotle. If you wanted, in his time, the English of the time, so to speak, was the language of science, and scholarship was Latin. You want to study, you have to learn Latin. So he taught himself Latin, and he started reading Aristotle. And he started writing, he wrote 2 theses about, one Aristotelian metaphysics, and the other one is about Aristotelian logic and the law. In fact, he was so young when he wrote his thesis that the university refused to give him a doctorate because he was too young to receive a doctorate. And he discovered Lull. He wrote, when I was young, I found pleasure in the Lullian art. And out of the Lullian circles, he came up with a much more ambitious dream. And this is at age 20, mind you. And the dream was a universal mathematical language, which he called lingua characteristica universalis. And this will be a language in which you can express all human knowledge. So one is a universal language, and second, calculational rules. He called it calculus ratiocinator, reasoning calculus, where you can derive logical relationships. So again, you can mechanize reasoning. And he wrote, if controversies were to arise, there will be no more need of disputation between two philosophers than between two accountants. For it suffice to take their pencil in their hands and say to each other, calculemos, let's not calculate. So if philosophers want to argue, they need to put their assumptions and just crank the calculus ratiocinator and see what comes out of it. And if you think that maybe Leibniz was naive, Leibniz actually was not just a philosopher. He built mechanical calculator that could do multiplication, for example, okay? So he had this dream in amazing early that reasoning could be mechanized. Leibniz did not get to carry his dream very far. Unlike Newton, who was a professor in Cambridge, Leibniz was the librarian for the Duke of Braunschweig, and his main job actually was the family tree of the Braunschweig family, and so he was very busy with that. And he wrote a lot, but much of what he wrote was not published in his lifetime. The story is that when he died, the only person who attended his funeral was his secretary. Much of what he wrote and his fame came in the 20th century. Only really then, much of what he published, much of what became published only in the 20th century. So he did not get to carry out his idea very far. And now we jump about 100+ years after Leibniz, and we meet George Boole, who described of a man of acutist intellect and manifold learning. George Boole was, his father was a shoemaker. And in 19th century England, if you were born to a family of a shoemaker, most likely you're going to become a shoemaker. But he was very, very bright. He was self-taught. He taught himself Latin. In fact, at age 12, his father got into a fight with the headmaster of the school because Boole translated an ode by Horace from Latin to English. And the translation was so good that the headmaster could not believe that a 12-year-old would do it, and he accused him of some kind of plagiarism. So Boole taught himself mathematics, started tutoring teachers in mathematics, and without any formal training in mathematics, ended up being a professor of mathematics in a University College Cork in Ireland. And the 19th century is a century of the rise of abstract algebra, all kind of things of algebra that we are familiar with today, group theory, fields, rings, all of these are development of the 19th century. And Boole has the idea that if you look at the syllogism of Aristotle, they're all about classes of objects. And these classes of objects can be treated algebraically. So for example, when we think about, let's say, white sheep, what do we mean? We mean take the class of white things and take the class of sheep and take their conjunction, and that gives you white sheep. And he says this is a form of product operation. So Boole says we can think of logical conjunction and as a product operation. We can think of a logical or as an addition operation. So now we have an algebraic structure. So this gives rise to what we call today Boolean algebra. He published a book in 1847, The Mathematical Analysis of Logic. What was his goal? His goal was amazing. The design of the following treatise is to investigate the fundamental laws of the operations of the mind. So we are still discussing today. In fact, I heard a World Logic Day lecture at 10 o'clock by Georg Gottlob in Vienna, and he discussed machine learning versus symbolic logic. So Boole believed that the way the mind works is logically. So doing logic is doing cognitive science. You can think of Boole as the first cognitive scientist. Of course, today we understand that the brain the intelligence is much more complicated than just logical thinking, but Boole wanted to find the fundamental laws of the operations of the mind. In 2017, I visited University College Cork, and I was taken to the library in which they have the Boole collection. And it says, we have here Boole's personal copy, annotated by him, of his own book. Would you like to hold it? And I said, of course. I mean, the only thing I would like to hold more than that will be the tablet that Moses broke when he came down from Mount Sinai. So I'm holding the book in my own bare hands. I'm amazed that they didn't ask me to put gloves on. So I held the book and looked through the book of Boole's personal copy of his own book. And then for a week, I didn't wash my hands because I touched Boole's book. So what Boole was able to show is the connection between algebra and philosophy. How is that? For example, Boole said that logical conjunction and is what we call the idempotent. So white is equivalent to white and white. So we have a new axiom, x equal x times x. So multiplication is, this is x squared equal x here. He says, well, now we can manipulate it the way we're doing in algebra. If x equal xx, that means that x minus xx is 0. And now we can factor out x. It means x times 1 minus x is 0. What does this say? It says, if you try to make something, if something is both in the class white and not white, that's a contradiction. And in fact, the principle of contradiction is the most fundamental principle in philosophy. So the Greeks argue about what we call the excluded middle. Does something have to be either true or false, either in between? But clearly something cannot be both true and false at the same time. You cannot be white and not white at the same time. So Boole argued that this algebraic equation expresses the principle of contradiction, which Aristotle described as the most fundamental axiom of all philosophy. So the algebra have philosophical meaning. Boole is another character that doesn't get to carry out his dream very far. He died at age 49. He went to his lecture, he trained, he became soaking wet, he caught pneumonia, he came home with fever. His wife was taught that the remedy for a disease has to be similar to the cause. So she put him in bed and poured on him a bucket of ice water. And unfortunately, that did not help, and he did die from pneumonia. At relatively, I said, a young age of 49, he died from pneumonia. His work was continued by another British logician, William Stanley Jevons. Jevons was also an economist, but an economist, I say, his reputation is mixed because he believed that the economic cycle of boom and bust is connected to sunspots. And this is not something that we believe today. But he was very significant as a logician because he followed up on Boole's work. In fact, Boolean algebra that I mentioned before were not really invented by Boole. They were developed by Jevons, who called them Boolean algebra to honor Boole. Boole did things differently. There was some technical problem with what Boole did. Boolean algebra are really the creation of William Stanley Jevons. Jevons was also interested in mechanizing logic. Remember this dream that goes back to Lull, mechanizing reasoning. And he actually built a machine that can reason. Then the machine was very primitive. It's sometimes called the logic piano because it has a bit of a shape of a piano. It could only reason about 4 logical propositions, so not very advanced. But he did it all with moving wooden pieces. So don't underestimate the sophistication of this machine. So the first logic machine, remember the concept of calculus ratiocinator by Leibniz. The first realization of that comes from 1870. Jevons built the logic machine, logic piano. And as primitive as it was, he goes on to write about the implications of this. So what is the motivation? He realized that logical reasoning is hard. And we know it today. There are deep connections between logic and computational complexity theory that I will not talk about today. And he writes, I have given much attention, therefore, to lessening was the manual and the mental labor of the process. And I shall describe several devices which may be adopted for saving trouble and risk of mistake. He was very excited about it. As I awoke in the morning, the sun was shining brightly into my room. There was a consciousness on my mind that I was the discoverer of the true logic of the future. For a few minutes, I felt such a delight, such as one can seldom hope to feel. I always show this quote to my PhD student, and I said, you have to be that excited about your own work. And I remember, this is a machine that can reason about 4 Boolean variables, 4 bits, if you want 4 bits. And yet he writes, the machine represents a mind endowed with power of thoughts, but wholly devoid of knowledge. It cannot be asserted, indeed, that the machine entirely supports the agency of conscious thought. So you can see that these questions about, if you want, artificial versus natural intelligence, is a question that is not just being asked today. It was already asked in the 19th century by the very, very early pioneer of computing. And we'll see another example of this. The last comment I find is quite ironical. He writes, I must remark that these mechanical devices are not likely to possess much practical utility. We do not require in common life to be constantly solving complex logical problems. I mean, this is a well-known phenomenon in science, that the scientists who discover, or scholars, they discover things, they may not always realize this full significance of this. There is a story about when the Cavendish lab in Cambridge, when they discovered the electron, they were very proud. They had a party and they had a toast to the electron. May it never be of any use to anyone. But could not conceive how anyone could take advantage of somehow of electrons. Who cannot use electrons? So again, Jevons did not realize that logic machine might be useful one day. And in fact, my argument is logic machine led us to the iPhone. So how did we go from logic piano, which was so primitive, and even its inventor did not think that much can be done with it, to the iPhone. So where does the relevance of logic to computing, where and when was it born? And the standard attribution is to a very bright young student, Claude Elwood Shannon. He's one of the few people here that you can see that live to live long and mature life. So he's an exception here. We'll see another one. Now, Shannon is mostly famous for information theory. But he did information theory about the theory of communication when he was old, when he was 32. What did he do when he was young, maybe 21? So he wrote a master thesis at MIT. And the master thesis was called a symbolic analysis of relay and switching circuits. And Shannon made the case that there is a tight connection between circuits and switches and logic. Why? Because a switch can be on or off. And he says on correspond to Boolean 1, true, and off correspond to Boolean 0, false. And circuits will be connected in a series. And then it's correspond to a logical conjunction. Or they be combined in parallel. And then it corresponds to disjunction. Or, so this deep connection between logic and electronic circuits was made extensively in this beautiful thesis by Shannon from 1937. Herman Goldstein, who was the project manager for the ENIAC, the first programmable computer, electronic computer, which we are going to hear about more later in the talk, or this thesis helped to change circuit design from art to science. Howard Gardner at Harvard wrote possibly the most important, also the most famous master thesis of the century. But it turns out that this is a little bit rewriting of history. When you go to the ENIAC developers, which was in the 1940s, they were not aware of this master thesis. Master theses at the time were not widely published. You know, today you can find it on the web, but you couldn't do it in the 1940s. You didn't know about the master thesis written at MIT. But it turns out that the idea, the connection, this idea of connection between logic and computing goes back to the 19th century. And there we're going to meet Charles Saunders Peirce. a figure of, described as a figure of mysterious greatness, the greatest intellect, some people wrote, the Americas have ever seen. He was a mathematician, an astronomer, a chemist, a geodesist, a surveyor, cartographer, meteorologist, spectroscopist, engineer, inventor, psychologist, philologist, lexicographer, historian of science, mathematical economist, lifelong student of medicine, book reviewer, dramatist, actor, story writer, phenomenologist, semiotician, logician, rhetorician, and metaphysician. Of course, all this in his spare time. So an amazing character, and we can talk a lot about Charles Saunders Peirce. But I want to mention his student first. In 1886, Alain Marquand, his student, publishes an article in the Proceedings of the American Academy of Arts and Science. It's a distinguished private academy, and they had a publication. And the paper by Marquand was a follow-up on Jevons' paper. Jevons published about a logical machine, and Marquand described a new logical machine, a new design. The article caught some attention. Charles Kendall Adams, who was then president of Cornell, wrote, "Dear sir, please accept my thanks for a new logical machine. Could you invent a machine that would do the work of a college president? I give you my order in advance." So we have a logical machine, and towards the end of the year, Peirce writes to Marquand, and he said, it's time to build a machine for very difficult mathematical problems. So again, he's suggesting that we can use logic machines to do computing. He said, I think electricity would be the best thing to rely on. And he goes on to do multiplication and addition in logic. So between Peirce is conceiving that if you can do logic, you can do computation. Marquand did not build such a machine, as far as we know. There is no evidence he built such a machine. But Peirce had this idea, logic is intimately connected to computation. And he goes on to think about this implication. And he writes, 1889, a logical machine is a machine which, being fed with premises, produces necessary conclusions from them. Okay, logical inference. This is obvious. But here comes the next line. The value of logical machine seems to lie in showing how far reasoning is a mechanical process. So reasoning can be mechanized, and two, calculating machines are specialized logical machines. So Peirce is saying reasoning can be mechanized, and if you can do mechanized logic, you can mechanize computation. So these ideas of mechanization, you can see it's already rising in the 19th century. And of course, you also know about Charles Babbage, but Babbage's idea really did not have much impact at all in his lifetime. These ideas, we will see, will have more impact. And again, Peirce is starting to think as a philosopher, precisely how much the business of thinking a machine could possibly make to perform, and what part of it must be left to the living mind is a question of without considerable practical importance. Again, the boundary between artificial and natural intelligence is a question already being asked in the 19th century. Now, until now, I talk about mathematical logic in the sense of using mathematics to explore logic. This is what Boole has done. Boole brought algebra to logic, which was a huge contribution because logic became now a branch of mathematics. But mathematical logic has another meaning in which you use logic to study mathematics. And this will be the theme of the rest of this talk, bringing logic into mathematics. And for this, I'm going to start by quoting from a very, very famous article by Eugene Wigner, who got a Nobel Prize in chemistry in 1963. He wrote an article called On the Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he started by quoting many scholars before him. Euclid, the laws of nature are but the mathematical thoughts of God. Wow, what a beautiful, beautiful sentence. Galileo, the universe cannot be read until we have learned the language and become familiar with the character in which it is written. It is written in a mathematical language. Descartes, I allow no hope for principle in physics other than those hidden in geometry or in abstract mathematics. And so we see that through the generation, people thought that mathematics is the right way to describe nature. And that's, Wigner shows many examples where you develop mathematics, and then it turns out to be just appropriate for describing nature. And he concludes with the empirical law of epistemology. It's empirical, it's an observation that the mathematical formulation of the laws of nature is both appropriate and accurate. Mathematics is the correct language for formulating the laws of nature. And that's really how science today works. You want to be a physicist, you use mathematics. You want to be a chemist, you need mathematics. Biology is more complicated, but even there, people more and more are using mathematical tools to describe life. But this observation raises deep philosophical questions. Albert Einstein asked, how can it be that mathematics, being after all a product of human thought, which is independent of experience, that's something one can argue, is so admirably appropriate to the objects of reality? How does mathematics connect to nature? Mario Livio wrote a book asking this question, is God a mathematician? But we need to ask another question. What's so special about math? Why is math playing such a special role in natural sciences? Again, Albert Einstein. One reason why mathematics enjoyed special esteem above all other sciences is that its propositions are absolutely certain and indisputable, while those of all other sciences are to some extent debatable and in constant danger of being overthrown by newly discovered facts. In fact, Albert Einstein did not receive his Nobel Prize for general relativity because it was not yet confirmed experimentally. So it was beautiful mathematics, but is it true? It was not clear. So this raises another question. Why is mathematics so absolute? What is special about mathematics? And the answer is, we all know it, mathematics has proofs. No other discipline has a concept of a proof, of an airtight proof, which has been called the high road to truth. As far as you know, this notion of deductive proof, it's a discovery of the Greeks in the classical period. And when they discovered this airtight argument, they thought it was so magical, it must be a gift from the god. When Pythagoras discovered the proof to Pythagoras theorem, they slaughtered an ox to thank Apollo for this amazing gift. To understand the importance of proof, we should go to the most influential mathematicians of all time, Euclid, who lived in the 4th, 3rd century BC. He is not considered the best mathematician of all time. This title is reserved to Archimedes. But Euclid wrote a textbook almost 2,500 years ago. And you almost surely studied from his textbooks, maybe some new version, a modern version. He wrote Elements, which was a textbook in plane geometry or Euclidean geometry. And we still teach high school geometry that way, essentially. So if you think about your high school mathematics, there were two branches. One was geometry, which was a logically perfect science. Everything had to be deductive and airtight. In fact, it was so beautiful that on the gates of his academy, Plato wrote, "Let no ungeometrical person enter here. You want to enter my academy, first you need to study geometry." But in high school, you also study algebra and calculus. And calculus in particular were a bunch of recipes. Why? Well, do it because I'm telling you so. We didn't have solid, airtight foundation for calculus. And so geometry was considered to be the queen of mathematics for many, many, many years. In the 19th century, we have a reversal. First, people discovered non-Euclidean geometries. So suddenly geometry is being dethroned from its place in mathematics. It's the only possible geometry. There are other geometries. And by collective effort of many mathematicians, Bolzano, Cauchy, Cantor, Dedekind, and Weierstrass, finally the calculus was fully formalized in terms of just a bunch of recipes with the full formalization. Today we call it analysis. But at the heart of this formalization lies the infinite, because calculus is about the infinitely large and the infinitely small. The limits, either you go to infinity or you go to zero, infinitely small. And this extensive use of the infinite raises a very central issue, a very problematic aspect of mathematics. Well, mathematics has proofs, but can we agree? Can we be precise? What is a rigorous proof? We all talk about a rigorous proof. What is a rigorous proof? Especially if the infinite is hiding in the middle of our proofs. And the infinite has been very problematic in mathematics and philosophy for a long time. In philosophy, it goes again all the way to Aristotle, who said infinitum actu non datur. There's no actual infinity. Yes, you can count numbers, and you can never stop. You can say +1, +1, +1. But he refused to say there are infinite many numbers, because no human have access to infinite many numbers. But St. Augustine said, wait a minute, people don't have access to infinite many numbers, but God looks at them and God can see all the numbers. So God has access to the infinitude of numbers. So how can you say there's no actual infinity? Amir Axel wrote a wonderful book called The Mystery of the Aleph. Aleph is a mathematical symbol for infinity in terms of cardinal numbers. He wrote, first discovered by the Greek between the 5th and the 6th century BC, the concept of infinity was so overwhelming, so bizarre, so contrary to every human intuition, that it confounded the ancient philosopher and mathematician who discovered it, causing pain, insanity, and at least one murder we know of. One student of Pythagoras was murdered by drowning because of a mathematical dispute about rational numbers. But this philosophical debate in the 19th century becomes a mathematical debate. Cantor in 1874 proves, using self-reference, again, remember self-reference? Cantor using self-reference, that there are infinitely many different infinities, which is again, mind-blowing. What does it mean? Infinitely many different infinities. And we see, again, mathematicians over the years arguing about it. Leibniz loved it. I'm so in favor of the actual infinite. Instead of admitting that nature abhors it, I hold that nature makes frequent use of it everywhere. Gauss hated it. I protest above all the use of infinite quantity as a completed one, in which mathematics is never allowed, verboten, not allowed. Kronecker, when he saw the Bolzano-Weierstrass theorem that uses the infinity, the actual infinity, said, obvious sophism. And Kronecker called Cantor a charlatan. Hilbert loved it. No one shall be able to expel us from the paradise that Cantor created for us. So today, higher set theory, which deals with infinities, is called the Cantorian paradise. And Frege wrote, for the infinite will eventually refuse to be excluded from us arithmetics. Thus, we can foresee that this issue will provide for a immense and decisive battle. And there was such a battle. The battle happened in the 20th century, and it was a huge mathematical battle, not a physical battle, between two great mathematicians. Hilbert, we'll meet Hilbert shortly, and Brouwer. And it became a very bitter, very personal fight. In fact, what happened, Hilbert was the editor-in-chief of Mathematische Annalen, and he blamed Brouwer for trying to destroy mathematics, but not allowing concepts as infinity in proofs. And he tried to expel him from the board, and it became a huge controversy. And he told all the editors, you must take a position. You're either with me or against me. And all the editors first compelled to join the fight, except for one editor, Albert Einstein, who said, I refuse to get involved in a war between the mice and the frogs, referencing a classical Greek comedy. So now we're going to meet Frege. Frege was described by some people as the second most important logician after Aristotle. Again, I think everybody agreed on the priority of Aristotle, but the second one can debate. Some people think that Gödel maybe was the second most important one. So what was so important about Frege? So Frege was trying to think, again, he said, we need to put mathematics on more solid foundation. And first we need to understand what is the language of mathematics. And he wrote a small book in 1871 called Begriffsschrift, in English, a language for concept. And he argued that these, remember, Leibniz wanted a universal language for all human knowledge. And Frege says, we have such a language at least for all of mathematics, because he said every mathematical domain is about mathematical object, maybe numbers, relationship between them, 2 less than 3. They're called predicates, operations on them, 2 plus 3, the logical operation, and or not. And he also introduces, actually, we'll see in a minute, he uses he did not introduce quantifiers. We will see shortly who introduced quantifiers. But the quantifier for all there exists and the like. So you can take the Aristotelian syllogism, all men are mortal, and you can be more formal and say for all x, if x is a man, then x is mortal. And today we write it in a logic we call first order logic. We use the inverted A as a symbol for all. So this is for all x. You read it as follows: for all x, man of X implies mortal of X. If X is a man, then X is mortal. So now we have a universal language to describe all of mathematics, and the quantifier are also, remember Charles Saunders Peirce? He's one of the people who introduced quantifier. He said we need to go beyond Boolean connectives. We also need quantifiers. In an important anthology written in 1967, from Frege to Gödel, describing the development of logic from Frege to Gödel, von Hayernuth, who wrote it, right, Begriffsschrift is perhaps the most important single work ever written in logic. Again, I think I would beg to differ. I think that Organon, which was Aristotle's book, was probably the most single work ever written in logic. Maybe this is number 2. Now Frege is working on a follow-up book. We are in the 20th century, and now enters the picture Bertrand Arthur William Russell, a British philosopher. Here we're seeing the old Bertrand Russell, and you can see that he lived to very old age. He lived to 98. He's the oldest living kind of logician in this story. But when we enter our story, he's still young. He is about 30 years old, and he writes a letter to Frege. And the letter starts very nicely, very politely. I find myself in agreement with you in all essentials. I found in your work discussion, distinction, definition that one seeks in vain in the work of other logicians. There is just one point where I've countered a difficulty. But the difficulty, they had a long exchange of letters, and eventually Frege was convinced that this was genuine difficulty. And the difficulty was that Russell found a contradiction in Frege's system. We'll see details in a minute. Frege published his book, the book that was about to come out. He published it, but he had an appendix. And he wrote an appendix. There's nothing worse that can happen to a scientist than to have the foundation collapse just as the work is finished. I've been placed in this position by letter from Mr. Bertrand Russell. So in the appendix of the book, he said, everything you have read until this point is wrong, because of what we call today a bug found by Bertrand Russell. For Frege, from Frege's point of view, Frege was trying to base mathematics on logic. It was called logicism. He said all of mathematics can be based on logic. And then Russell did such a shattering blow to this life work that at the end of his life, Frege was in despair. He became extreme right-winger, opposed to the parliament, to democracy, to liberal, to Catholic, the French, and above all, he became a virulent anti-Semite. So what is Russell's paradox? So the central concept in Frege's work is the concept of a set, a collection of objects. And Russell asked, what is the collection of all sets that do not include themselves as a member? Is this a set or not a set? Now, this sounds like a bit of a mouthful. The collection of all the sets do not include themselves as members. So this sounds like a mouthful. So Russell gave a nice parable. He said, suppose you have a small town, and there is a male barber, and the male barber shave all those men, and only those men who do not shave themselves. So now we look at, there are men who shave themselves, and there are men who shave by the barber. What about the barber? If the barber shave himself, then he shouldn't shave himself. But if he doesn't shave himself, then he should shave himself. So we have, again, this is very similar to the liar's paradox. And we can say that Epimenides, after a slumber of 2,500 years, has spoken from his grave. And we have found, Russell found a contradiction in the foundation of mathematics. This became known as the foundational crisis. So Russell was determined to try to address this crisis. Something can be done. We cannot leave mathematics with a contradiction in its foundation. So Russell says, I'm going to try to do something about it. And he embarks on the project became known as Principia Mathematica. It was an incredibly ambitious project. Russell wrote, every morning I would sit down before a blank sheet of paper. Throughout the day, with a brief interval for lunch, I would stare at the blank sheet. Often when evening came, it was still empty. It seemed quite likely that the whole of the rest of my life might be consumed in looking at that blank sheet of paper. So he had writer's block. He could not see his way forward. And eventually, he sought help from his colleague, Alfred North Whitehead. And together, they wrote Principia Mathematica. Took them 10 years, 3 volumes, 2,000 pages. And they show how you systematically can derive all of mathematics from logic. avoiding all the obvious paradoxes. It was such a monumental effort that Russell wrote, "My own intellect never quite recovered from the strain of writing it, this 3-volume. I turn aside from mathematical logic with a kind of nausea." So I always tell my PhD students, there is a moral from it. Don't write a dissertation of 2,000 pages because it may cause you nausea. So now Russell claimed to have a resolution of the problem, of the crisis, but he did it by using 3-volume, 2,000 pages. Who knows how many contradictions? Begriffsschrift was a small book, and Russell found a contradiction. What about the 2,000 pages of Principia Mathematica? Can we trust them? And people say, we don't see why we can trust them. So into this crisis entered David Hilbert, who was around the turn of the century, the king of mathematics. In the 1900 Congress of Mathematics, David Hilbert presented a list of 24 problems that became the charter for mathematics in the 20th century, solve Hilbert's problems. Hilbert was a legendary mathematician. There are many, many stories about them. My favorite one, which is a bit grim, one of his students died relatively, rather by surprise, by a sudden disease. And there is a funeral, and Hilbert is asked to come and give the eulogy. And Hilbert stand up, take off his hat, and say, "Ladies and gentlemen, I'm crestfallen by this early death of my students. You know, at the time of his death, he was working on a problem in function theory. In particular, we're doing the theory of meromorphic functions." And he goes on over the grave to give lectures in function theory. So for him, talking about his students' mathematical work seemed completely appropriate. So Hilbert, after World War I, Hilbert decided we need to launch a program. The term Hilbert's program is a term we use later, but Hilbert says we have to try to resolve the foundational crisis. He says we need to formalize mathematics, prove that it is consistent, there are no paradoxes, it is complete, all mathematical questions can be answered one way or another. And finally, mathematics, this is where computing gets in. Mathematics is decidable. There is a mechanical way to decide the truth of every mathematical statement. So Hilbert talks about logical properties, consistency and completeness, but decidability is also an algorithmic property. So we see that the lead from philosophy, mathematics, also to computing, but talking about decidability, it's about computing. And Hilbert he wanted to dispose of the foundational questions once and for all. And he said, every mathematical problem must necessarily be susceptible to an exact statement, number one. And he said it has to be also computational. Once a logical formalism is established, one can expect that systematic, so to say, computational treatment of logic formulas is possible. So we should be able to answer all questions computationally. The final quote is just very beautiful because it's about his frame of mind. He said, why he believed in completeness. He said, every mathematician certainly shares the conviction that every mathematical problem is necessarily capable of strict resolution. We hear within us the perpetual call, there is a problem, seek its solution. You can find it by pure reason. So Hilbert has this program, and in 1930, he has retired, and he's from Königsberg. He's invited to be an honorary citizen of the city. And on September 8, I want you to pay attention to the date. September 8, he gives a radio address on the natural philosophy and logic, and it ends with the famous 6 words. Wir müssen wissen, wir werden wissen. We must know, we shall know. In mathematics, he said there's no unknowable. We must know, we shall know. And these words are engraved on his grave. Remember, September 8. We'll come back to the date in a minute. But the 3 legs, remember the 3 legs of Hilbert's program, consistency, completeness, decidability. The 3 legs are shattered in the 1930s. Gödel destroys completeness and consistency. He proved incompleteness, and he showed that you cannot prove consistency of mathematics mathematically. And the final leg, decidability, was destroyed by Church and Turing to show that logic, first of all, logic is undecidable. So Hilbert's program was beautifully posed, and in a few years, it has been completely destroyed. And the first two legs to be destroyed is by Kurt Friedrich Gödel. As a boy, he was known as Der Herr Warum. He always asked questions. Warum means why, and he always had a question: why? And so this is Gödel. Gödel was a docent in Vienna, and in 1940 he managed to escape to the United States to the Institute of Advanced Studies, where he became a very good friend of Albert Einstein. The story was when Albert Einstein and Kurt Gödel were walking to work and back from work at Princeton, nobody ever dared to interrupt the conversation by Einstein and Gödel. So remember, we saw that on September 8, Hilbert says, we must know, we shall know. But on September 7, Gödel destroyed the program. Gödel wrote, there might be sentences which are true, but not provable in a formal system. This is incompleteness. And it followed you cannot prove concept of mathematics mathematically. For Neumann, who was a rising star at that point, was in Göttingen, he was working on the concept of arithmetics. And immediately he understood that he was wasting his time. And he said, I will leave with logic. I don't want nothing more to do with logic. This is 1930. Amazingly, in 1929, Hermann Weyl gave a series of lectures in which he argued that we are very close to solving the problem and proving the consistency of arithmetics. Amazingly, where did Weyl give his lecture? He gave them at the Rice Institute in 1929. Rice became a university in the 1960s. Until then, it was an institute, technical institute. And Hermann Weyl was here at Rice University and gave a talk about the consistency of mathematics and says, we're just about to solve the problem. We're very, very close. There are insignificant gaps. And a year later, Gödel destroyed the program. Just as kind of stepping outside, remember at that point, the 1930s, Göttingen is the mecca of mathematics. It is the best math department in the world. Excellence has been over 100 years. But by 1934, almost everybody has left Göttingen. The Minister of Education, the Nazi Minister of Education, Bernhard Rass, is having is dining with Hilbert, and he asked, how is mathematics in Göttingen now that it is free from Jewish influence? Because if you're Jewish, you had to leave. If you're Jewish French, you have to leave. If you have a Jewish spouse, you had to leave. And Hilbert famously said, there's no mathematics in Göttingen anymore. So Göttingen was supposed to be the best math department in the world. And between 1930 and 1934, the specialness was gone. It was all destroyed. Now we jump into, remember, there were the two legs were destroyed by Gödel. The last leg is Church and Turing. What many people do not know about Turing, that Turing had Asperger's syndrome. And that means that his behavior, it's very ironic. A few years ago, I wrote a column, asked, would Turing have won the imitation game? If Turing tried to pretend a human, you know, the imitation, what we call the imitation game, the Turing test, would Turing have passed the Turing test? And my answer is, based on the evidence we have, that he most likely would have failed the Turing test because he was so peculiar that people would think of him as a machine rather than human. Think of Sheldon on Big Bang Theory, that some people say, is he a human or is he a robot? Well, Turing was a little bit like that. So in a short number of years, in the 1930s, a bunch of mathematician logicians, Church, Gödel, Kleene, and Post, give birth to computer science. And it comes from mathematics, because the question that they were asking, what is a proof? And the answer they came up with, a proof has to be something that is so rigorous, that is so airtight, that it should be machine checkable. The creativity is coming up with a proof, but checking the proof should be machine checkable. Now you have to define, what does it mean? You have to define computation. So all the basic concept in computer science were all came up in these first few years there were no computer science yet. These were all logicians, mathematicians. The concept of algorithms, hardware versus software, concept of universal machine, concept of programming language. All were born in the 1930s by exploration in the foundations of mathematics. So mathematics, logic, and mathematics gave rise to computer science. None of these people were building computers at the time. They're all mathematicians. But this is now in the mid-1930s, now 36, 37. Within a few years, about 10 years later, computers will be built. This is the picture of the ENIAC, who was turned on in February of 1946. In fact, we will have next month, we will have the 75th anniversary of the ENIAC. Here you see Betty Jennings and Frances Bilas programming the ENIAC. Programming then was not writing code. It was setting switches and connecting cable. It required enormous level of patience and precision. And the conventional wisdom at the time was that only women have the precision and the patience to do programming. Only later, when programming became coding, it became easier, and then men took over. And now we come back to, remember, we met von Neumann when he's hearing about the incompleteness theorem, and he decides to leave logic. At that point, he's a rising star. Now we are now in a few years later, he's not a rising star anymore. He is a big star. He's a great mathematician. In fact, he's considered the last of the great mathematicians who were the king of mathematics. After Hilbert, it was von Neumann. No one else after that had the same stature as these two mathematicians. At that point, he did the mathematics of quantum theory, turbulence, game theory, and so on and so forth. Now, how the ENIAC was not a project of von Neumann. The ENIAC was a project of the US Navy. You need to calculate ballistic tables. It was built by engineers. There was very little theory behind it. But in August 1944, von Neumann is standing in a train station in Aberdeen, Maryland. And Hermann Goldstein, who is the project manager for the Navy, sees von Neumann and goes to him and says, hello. And von Neumann, as an atypical mathematician, was actually rather friendly, and they start chatting. And von Neumann asks Goldstein, what are you working on? And Goldstein says, well, we're building a computer. And von Neumann says, this is exciting, I want in. And no one could tell him no. By the time he joined, the design is done. They're just building the ENIAC. So they're designing the follow-up, the EDVAC. And von Neumann is writing in 45 and 46 two incredibly important memoranda that describe how to build electronic computing instruments. And it's clear that he did read papers in logic because these designs are based on Boole's and Turing's idea. And to this very day, we call modern computers von Neumann machines because they're based on von Neumann basic architectures. And he already in 1945 understood the implication. Today we worry about social media, is it destroying us? Von Neumann wrote in 1940 of AI. Von Neumann wrote in 1945, what we're creating now is a monster whose influence is going to change history, provided there's any history left. So by the 1950s, people were building computers. They were called Joniacs because they're based on John von Neumann's design. They are reasoning machines. Leibniz's dream has come true. Remember, calculus ratiocinator. We started from reasoning. We discovered patterns of reasoning. We gave rise to logic. Logic gave rise to computing. And now we close the circle. We have computers that can reason. And the tight connection between computer science, logic, and computer science has continued since then, so much so that some people call logic the calculus of computer science. And Martin Davis, a very senior, very distinguished logician, wrote already in 1988. He wrote, when I was a student, even the topologists regarded mathematical logicians living in outer space. Today, the connection with logic and computers are a matter of engineering practice at every level of computing or computer organization. Tight connection between logic and computing. But I want to take one step back and remember the abstract talk about people who died young, miserable, or both. And Christopher Papadimitriou put it very nicely in a book review he wrote in 2001. He said, and then there is a human story, the unbelievable and total sadness of it. Leibniz never had a chance to advance his dream, and he was consumed by his famous row with Isaac Newton over the simultaneous invention of the calculus. Boole lived in poverty and died relatively young of pneumonia, having walked to his lecture through rain. Cantor died in deep depression, his ingenious work ignored. Remember, Kronecker called him a charlatan. Also, Frege's reputation survived only the fact that Russell found his system. It was marred forever by his vehement racism and anti-Semitism. Hilbert lived in 1943 in a strange denial of the evil that was destroying his country. Whereas Goedel fled to Princeton, were possessed by an advancing paranoia. He starved himself to death in 1978. He believed that someone is trying to poison him. He only trusted his wife's cooking. When his wife was hospitalized, he did the logical thing and he stopped eating. And as I said, he died on January 14, 1978. Still, the most tragic end is Turing's. His apparent suicide in 1954 was presumably because of persecution by the country that he served so brilliantly in World War II. He played a key role in breaking German codes, but in the 50s, he was being prosecuted for being gay and he committed suicide. And some people theorize that the bite in the apple here symbolizes Turing biting from a cyanide-laced apple. This is a speculative theory. I want to finish by relating this to say there is a connection to today's reality. Popper was a philosopher of science. He's very famous for the Popperian principle of what is science. Science has to be falsifiable. And Popper realized that the essence of Gödel's incompleteness is observation that too much truth leads to contradiction. And he realized that this has other implications. It led to what we call today the Popperian paradoxes. Unlimited tolerance leads to disappearance of tolerance because you tolerate the intolerant. Total freedom leads to suppression of the weak by the strong. Democracy allows a majority to decide to eliminate democracy. So we are still today struggling with the proper bound of tolerance and freedom and democracy. And it goes back to Gödel. There is a story that when Gödel was naturalized in the United States, he started telling the judge about that he found a loophole in the Constitution by which the US can become a dictatorship. And he did not elaborate. The judge did not want to go into details, and people always speculated. And so there are many speculations. And the one conclusion is that probably the Article 5 of the Constitution that describe how you can modify the Constitution, how can you amend the Constitution. In particular, you can also amend the amendment process. You can make it easier to amend a Constitution, ultimately leading to the dictatorship in the United States. So this history of logic and computing also has relevance to today politics. And I will close here, of course, with another self-reference. Thank you all very much.
Thank you. Thank you. That was fantastic. I guess we have several questions, and I don't think we have time for all of them. But, you know, I will go with one of them is there was a question that we went from philosophy to indisputable logics, but with deep learning and inability to explain AI, are we again going back?
So in fact, the interesting issue is that what is the connection today between logic and AI? And my colleague Georg Gottlob gave a talk at 10 o'clock today, in which partly he was addressing this question. So I think today we understand that when Boole thought that all the brain does is logic, we understand that this is naive. First, we have behavioral economics that demonstrated how irrational humans are. And even where rational, clearly many tasks we do, such as face recognition, we don't use logic to do face recognition. Some people refer to it by the fast and slow thinking of Kahneman. Clearly, the brain has two systems for fast thinking and slow system. And we do logic, but we do also other things. And the question is how to integrate them. And one of the hot trends today in AI is what they call neurosymbolic reasoning, which is how do we combine this deep learning, which is neural reasoning, with symbolic reasoning? Can we have a marriage between the two things that will give an advantage to this? I see that my sister in Israel has joined the show, so joined the talk. So hello there in Israel. Rivka Miller. Yes. Other questions?
So there are several other questions about, like about whether the slides will be posted. I think the talk is recorded, so we will, post the slides online. And if you're registered,
the talk will be the talk is recorded and it will be uploaded to YouTube. Yeah.
Yeah, and I think, we have too many questions getting in to answer, and I think we are almost about time anyway. So we'll end here. thank you all for joining, and keep looking for future events from us. Thank you. Thank you very much.
Bye-bye. Bye-bye, everyone.
Bye-bye.